So let's not forget about our third problem, eigenvalue or spectral problems. The thing that is completely different here compared to the first two problems is that our linear operator A goes from a vector space X into the same vector space X. Okay, so there is no Y here. Y is the same as X. That is different. So remember that in linear algebra you would always study eigenvalue problems for square matrices, not for rectangular ones. This is what is reflected here. So what was an eigenvalue? Well, let's see. So a complex number is an eigenvalue of A if there exists a vector x, but not the zero vector, that would be too easy, in x, such that A applied to x gives you a multiple of x, and that multiple is given by the factor lambda. Okay, and then x would be called an eigenvector. Why is x equal to 0 excluded? Well, x equal to 0 will always be subject to that equation here, no matter what lambda, so this is clearly not interesting. Do you remember how you computed eigenvalues and eigenvectors in linear algebra 2? Well, you took this equation ax equals lambda x, and then you rewrote this as 0 equals ax minus lambda x. Now the trick is to squeeze an identity matrix in here, because ix is just the same as x. So if you do this, then this says ax minus lambda identity x, and now you can just factor out a minus lambda identity, it's a minus sign, times x. This matrix here has the property that it turns a non-zero vector x into 0. So your eigenvector x is in the kernel of a minus lambda I. So the kernel of a minus lambda I is not just consisting of the 0 vector, or in other words, a minus lambda I is not injective. Okay, so we could take this as a characterization of eigenvalues. Let me just move this around a little bit. So we could say that complex number lambda is an eigenvalue of A if and only if A minus lambda I is not injective. Still, this is not exactly the way how you compute eigenvalues, but it's leading the way. So how do you check whether or not a matrix is injective or not? or how do you check whether or not the kernel is non-zero? So let's go back to your linear algebra course. So if the dimension of X is finite, let's say it is, let's call this little n. So for example, X is just Rn or Cn, then how do you check whether your matrix A minus lambda I is injective or not? Well, you look at A minus lambda I, which is then an n by n matrix. Okay. And the fact that its kernel is not zero means that your solutions are not unique. So you have multiple solutions. And the fact that you have multiple solutions means in Gaussian elimination you have free variables. When do you have free variables? Well, you have free variables if not every column of your matrix has a pivot. So after Gaussian elimination, you would have pivot elements sitting somewhere here along the main diagonal, but maybe not all the way. So some of these variables here would be bound variables, but some of them are free, and these are the ones where the column has no pivot element. The fact that you have free variables means that you have a kernel that is not just zero, so you have freedom in your set of solutions. So let's sum this up. So not every column of A minus lambda I after Gaussian elimination has a pivot element. But because this is a square matrix, it is as high as it is wide, you could as well say not every, instead of column, you could say not every row has a pivot, or you could as well say the rank of the matrix is less than n. Okay, well, let me write some of these down. So this is equivalent to the rank of A minus lambda I is less than n. This is equivalent to A minus lambda I is not invertible, and this is, however, equivalent to the determinant of that matrix A minus lambda I being equal to 0. Okay, and this is your point of attack in your linear algebra course, right? So this is where you start to compute the lambdas that turn out to be eigenvalues, and from there you compute the eigenvectors. We just observed something that looks interesting, because we started off by saying, or we observed that lambda is an eigenvalue if and only if A minus lambda I is not injective. And then after fiddling around with Gaussian elimination and counting pivots and so on, we saw that this is equivalent to the very same matrix A minus lambda I not being invertible. Not injective, not invertible, seems to be the same, well, at least for finite square matrices. The argument is, well, as we just went, in a square matrix, if every column has a pivot, then every row has a pivot, and if not, then not. So injectivity and surjectivity for square matrices always come at the same time, and that's why invertibility, or alias bijectivity, comes with already one of the two. Nevertheless, this property here is the starting point for a new definition. We say that the complex number lambda is a spectral value of A if A minus lambda I is not invertible. Okay, so you see that the property that we are pointing at with the red arrow here is the starting point of this new definition, which, as we just saw, turns out to be actually the same as eigenvalues, at least as long as you are in a finite dimensional setting. So let's write that down. So if the dimension of X is finite, then the words spectral value and eigenvalue mean the same. In general, however, these two words will not mean the same, otherwise you wouldn't need two words. So let's write that down. So in general, okay, so let's look at the two situations. The first situation is lambda is a spectral value of A. Okay, and let's compare that to the other situation. Lambda is an eigenvalue of A. So in the first situation, we just learned that A minus lambda I is not invertible, whereas in the second situation, A minus lambda I is not injective. You can clearly see the difference. This one is about injectivity, this one is about invertibility. So one implies the other. Which one implies the other one? Well, if you're not injective, then you can clearly not be invertible. So this direction must be true. The other one, probably not, otherwise we wouldn't need two different words. So let's try and understand that. Invertibility means injectivity and surjectivity, right? So not invertible must mean you're not injective or not surjective. Interesting. Okay, so if you're a spectral value, then you could be an eigenvalue because you're not injective. See this? Or you could be something else because you're not surjective. I mean, your means A minus lambda I. So this set of spectral values, which is also called the spectrum. So spec A is set of all spectral values lambda of A, which is a subset of the complex plane called the spectrum of A. So this splits into eigenvalues. So spectral values could either be eigenvalues or they could be something else. Okay, depending on whether A minus lambda I is not injective or not surjective. Okay, we saw that for the finite dimensional setting, this green case, the something else case, does not exist as a separate case. It's part of the blue case. So to convince you that in general this can happen, I should give you an example. So we need an example for an operator B from x to x, which is let's see, injective but not surjective. If then B is your A minus lambda I, then you have found value lambda where you are in the green case but not in the blue case. So indeed your lambda with one of these other points in the spectrum that are not eigenvalues. Where does this example come from? Well, it would be a bit too difficult to give you that as an exercise problem, I guess, because this is the very first infinite dimensional example, so we should do that together. And here is my hint. You take an operator B that takes an infinite sequence. Why infinite? Well, because clearly this has to be infinite dimensional, because in the finite dimensional setting this cannot happen, right? If you're injective, then you're surjective. If every column has a pivot, then every row has a pivot, because you're square. So let's take an infinite vector, so it just looks like a finite vector, but it never ends. Like this. And the operator maps this vector into a new vector that looks like this. It starts by 0 and then x1, x2, x3, and so on. So you're not really using information, you're just shifting everything one position to the right, filling the then empty first position with a 0. That's why this is called the right shift or the forward shift. Right shift or forward shift operator. I still want to give you a little exercise problem about this. You should think about this. Convince yourself that indeed this operator is injective but not surjective, and think about what space X could be used here to make this a proper example.